Okay, so I hope all of you had a wonderful week, right? So this week's tutorial is basically, focusing back on our tutorial. This week's tutorial is basically based on homework number 4, right? So the questions are already available on Moodle, um, and, uh, and the solution has been uploaded, right? So please go through them. But let's start with this week's tutorial. So I'll be discussing the solution that has been provided, right? So this should be homework number 4. So let's start with this week's tutorial. Problem number 1, a frequency hop spread spectrum, right? So FHSS is a frequency hop spread spectrum system, uses a MFSK. So this MFSK indicates a multi-frequency shifting, right? Multi-frequency shifting. The data to be transmitted and PN sequence are given below. If the data rate is 3 kilobits per second and the baud rate is 1 kilosymbol per second, and the PN sequence bit rate is 2 kilobits per second with a hop occurring every 2 bits, right? What is the duration of the single bit, right? So the duration of the single bit, we know that the data rate is 3 kilobits per second, right? Based on this, um, we can calculate the duration of the single bit, right? So the duration of single bit is basically given by 1 upon data rate. So 1 upon data rate is equal to 1 upon 3 kilo, right? 1 upon 3 kilo. So which is equal to 0.333 milliseconds, right? Or basically 1/3 milliseconds, right? Uh, let's move on to part B. What is the duration of this single symbol? So duration of the single symbol, right? So the symbols are basically associated with baud rate. So baud rate is given as 1 kilosymbol per second. So in order to find the duration of a single symbol, we just basically do the same thing that we did for part A. So in this particular case, it will be time for single symbol is equal to 1 upon the baud rate, which is equal to 1 upon 1 kilo. Again, you are going to get 1 milliseconds, right? Uh, See what type of multi-frequency shift keying is being used. Value of m, right? So value of m, right? Remember, um, this is the function, right? 2 to the power of n is basically equal to m, right? Remember, we learned this about this uh, in our Nyquist theorem, I believe, right? Um, so using this, right? So based on this, we can calculate our n, right? Our n is basically the number of bits in a symbol, right? So based on this, if you see that one data rate is 3 kilobits per second, and the baud rate is 1 kilosymbol per second. So if you divide 3 kilobits per second by the baud rate, that is 1 kilosymbol per second, you'll get 3 bits per second, 3 bits per symbol, right? So what this indicates is there's 3 bits in each symbol. So basically, we are transmitting a 3-bit system, right? So in that particular case, this 3 over here is basically equal to our n. So in order to calculate our m, so we use this 3, right? This particular n that we obtain, right? We raise it to the base of 2, right? So that would be basically equal to m would be equal to 2 to the power of n. So n is 3. So 2 to the power of 3 is the number of levels. So basically, which is equal to 8. So 8 is the value of m, right? Which is equal to 8 FSK. Okay. So 8 bit, sorry, 8 level frequency shift keying, right? Let's move on to problem number 2. Problem number 2, it says consider the waveform shown in figure below. A, find an 8-level pulse code modulation communication system, right? So a 8-level pulse code modulation communication system. So in this particular case, it is somewhat similar to our you might have seen this in our ADC, isn't it? Analog to digital converters, we have something like this. So it is somewhat similar, but we are sampling at if we mean at 8 levels, so we are having basically 8 different signal values, right? In this particular case. So now IDC, the same thing happens, isn't it? So that is basically if we are having a 3-bit system, so if we need to convert an um, analog signal into digital, that is basically if we have a 3-bit system, that is basically having a 2 to the power of 3 number of levels, isn't it? So we'll be having 8 different values, right? Ranging from 0 to the maximum peak value. So likewise, for this 8 PCM, it is somewhat similar to our ADC, right? That you have come across in your previous courses, right? So it says a 8-level PCM communication system. So what that means is that we have 8 levels. So 1 is the first level, is the second level, third level, fourth, fifth, sixth, seventh, and eighth level, right? So altogether this makes up 8 levels, right? And uh, and this is the signal that is being transmitted, right, in the communication system. Now, uh, it says find an 8-level PCM communication system, right? 8-level PCM communication system. In order to find them, what you need to do is actually draw these straight lines in order to identify what example one and in what level does sample one fall in, right? So basically you draw a line, right? So if you draw a straight line, right? So you'll be ending with something like this, right? So what this means is at each sample, at what level does this communication or this particular signal falls in, right? This particular point. So like in our analog signal, if we have a 2 to the power 3 bits, so basically it starts from 0 and goes up till 7. That's the maximum value, isn't it? So same goes over here as well in our PCM system. You start with level 0 and you go up till level 7. So that makes up a total of 8 levels, right? So like I said, at each sample you take the lines up, right? Or you basically you're discretizing the signal, right? The signal that you have, and at each sample, what is the level that you have, right? That's what you need to identify, right? So if you draw all the lines, right, and if you discretize this particular signal, you'll see that this particular point, okay, for the first sample, sample 0, it basically uh, the disc point is this one, isn't it? So this point basically corresponds to level number 5, isn't it? So that becomes my level, or that's what that becomes my level sample, right? So like I was saying, at level at sample 0, this falls under level 5, so that becomes a district level, right? So this is basically having, or this falls at a district level 5, right? So sample 0 falls in district value of 5, right? Our digital value of 5. Then we do the same for S1. So this one, S1 basically falls at level 3. So again, this falls at, so at this corresponding sample, we write sample 1 is basically falls at a digital value of 3, right? So levels also indicate the digital values. So same thing we do for all samples that start from 0 to S9, right? That's what we are going to write. And each intersection, I mean, you have to identify at each intersections of this particular sample point, in what particular level does it fall under, right? Okay, so it starts from level 0 to level 7. So you do it for s is equal to 0 up to s is equal to 9. So if you do it for s is equal to 9, you can see for s is equal to 9, you can see this particular signal intercepts over here that falls at level number 0. So S9 has a value or the digital value of 0. Okay, PCM value of 0. Okay, so this forms my the this is basically my, or this is what I have identified as the 8-level PCM system, right? So this is what I have identified, which is basically discretizing the analog signal that we have for transmission. Okay. Moving on to question part B of this video question, it says find the PCM code and how many bits are needed to achieve a certain level of the code, right? So based on these, right, based on the values that we got over here, we now have to write a PCM code. We have identified the digital values that will be associated with each sample, isn't it? So basically we have identified t is equal to 0, t is equal to s1, right, so forth. We are going to have these particular values, right? This particular digital values. Now, uh, once you have these particular values, you can see the maximum value over here in this particular case is 7. And the maximum I mean, 7 value can be represented by a 3-bit system, isn't it? If you represent, if you use a 2-bit system, the maximum value you can actually cater for is from 0 till 3, isn't it? So if you use a 3-bit system, the maximum value you can cater for is 0 till 7, or if it is for 8 bits, right? Isn't it? In this particular case, the maximum value is 7. Okay, the maximum value is 7. So how many bits do we have to use in order to write the PCM code? We need to use 3 bits. Okay, so basically we need 3 bits to write our PCM code. So now for 0, right? So if we need three bits, uh, three bits, uh, 3 bits are needed to write PCM code. So basically 0 is represented by 0, 1 is represented by 0, 0, 1, 2 is represented by 0, 0, 1, and you write all the values up to 7, right? So this is the PCM code that we'll be using. Now write the stream of data that needs to be transmitted. So the data or the stream of code that needs to be transmitted is basically the values, right? Let's say the sample 0 value, right, falls in level 5. So the digital value that it will be transmitting will be the 5 value, right? So the 5 value represented in the digital form will be in the code form will be 101, isn't it? So that will be 101. The next one is sample 1. Sample 1 value is 3, right? So sample 3 value or sample 3 PCM value is 3, right? So corresponding PCM code for 3 is 011. So it will be 011. So you continue doing so. You write the code for 5, you write the code for 3, 1, 3, 6, 7, 6, 4, 1, 0. So based on this particular order, you correspond these particular values and write its code. So first one is 5, right? Going back over here, you can see 5, 3, 1, 3, right? 5, 3, 1, 3. So the first code is 5, 1, 0, 1, 3, that is 0, 1, 1, so 0, 1, 1. Next one is 1, 0, 0, 1, right? Then the next one is 3, 0, 1, 1, right? So we stop here. We go back to the table. We said and the next value is 6, 7, 6, 4. So 6 value is 1, 1, 0, right? Next one is 7, 1, 1, 1, right? 1, 1, 1. And then we have 6 back. So that is 1, 1, 0, right? We stop here. We go back to the table. What else value we have? We have 1 and 0 that is left, right? So we have 7, 6. Okay, we are left with 4, 1, 0, right? Sorry, we are left with 4, 1, 0. So the next code will be 4, 1, 0. So the value for 4 is 1, 0, 0. 4, 1, 0, 0. Next one is 1, 0, 0, 1, right? And the last value is represented by 0, 0, 0. So each particular value, right? Each particular value, right? Based on this particular value, that is 5. The corresponding code 5 is 1, 0, 0, 1. So that is written, right? And the, the order will be in this particular form. So first is 5, the code of 5 will be written, the next is 3, the code of 3 will be written, 1, the code of 3, 1 will be written, and so forth, right? Until you write the code for 0, 0, 0, right? So that is for writing the stream of data that needs to be transmitted. Moving on to the part B of this particular question, it says write the stream to be transmitted using the odd parity. So when we mean by odd parity, what we do is we check for the number of ones in our code, right? This is the code that we have, right? So we write the code, right, as it is. So we write the code as it is up till here, right? It's my code that I have created, or the stream that I have written that needs to be transmitted, right? So based on this, if I count number of ones, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16 ones, right? Okay, so I have 16 ones, right? And I have to use a odd parity. So what this means is I need to add an extra bit to either make, when I'm adding a parity bit, right? When I'm adding a parity bit, I'll either add 1 or 0 in order to make the system odd or even, right? So in this particular case, uh, I have 16 ones. So what that means is this system at the moment, if I add a 0, it becomes a even parity. So what I need to do is I'll need to add 1, right? The value of the last bit will be 1 in order to make in order to make this whole code to have 17 ones, right? Or to make this particular number of ones in this particular code to be 17, right? So basically, we actually, the last bit is our parity bit, right? So if we add 1 at the end, it makes the number of ones in this particular system odd. In that particular case, the system to be translated using odd parity will be this, right? So if you are wondering if I have written the same code or the code written over here, same code up till here, you can check over here. We have how many ones we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Again, we have 16 ones. So this particular code is written over here, right? So it's 16 ones in this particular system. So in order to make it odd, we add an extra bit of 1. If this whole system has 15 ones, what we had added over here is 0, right? In order for the system to remain odd, right? I believe you must have learned this in your CS1, isn't it? Yeah. Okay. So E, so part E of this particular question, or the last part of this particular question says find a frame check sequence, right? A frame check sequence of 7 bits and write the stream of code that is to be transmitted assuming T is equal to. So this is the polynomial to perform the calculation on the code over here that we have, right? And it says that we'll need to use the operation of modulo 2 arithmetic, right? So basically, we need to use the modulo 2 arithmetic when we mean modulo 2 arithmetic. Basically, we are using a XOR operation, right? Right. So basically, what this means is that the this means is that let's say we have an input A. Okay, let me just it's really hard to write, so I'll just show you the truth table of a XOR system. So XOR truth table, if you look up for that, right? So for a XOR truth table, you can see if I have two inputs, right, 1 and 2. So the XOR operation of those two bits will be if those two bits are like, it is going to result into 0, right? Two bits are like 1 and 1 alike, it is going to result into 0. If two bits are unlike, it will result into 1, right? So keeping that into mind, we'll perform the arithmetic, the modulo 2 arithmetic operation, right? In order to find a frame check sequence, what do we do? If it says we need a 7-bit frame check sequence, right? This is um, okay. First thing first, the frame check sequence is basically added to the transmitting data, right? It is added at the end of the transmitting data so that it indicates, right, at the end of the data, right? It's a large amount of data that you are transmitting. So this particular transmitting bit, right? This particular frame check sequence is at the end. Usually, what happens is this particular bits or this particular sequence allows us to check whether there has been some sort of error that has occurred in the transmitting data or not, right? So So basically that is the function of this frame check sequence, right? It is used to check whether there has been any error or not, right? So in this particular case, we have to do a write stream that is to be transmitted. So this is the arithmetic operation that is needed to code the data into 7 bits, right? We have to reduce the data or to perform this particular operation so that our data is in 7 bits, right? So that we find a frame check sequence that is of 7 bits long, right? That will be associated to the transmitting data at the end. And then we'll do at the receiver end, there will be a reverse operation or some other operation that will tell us whether we get whether the data has been corrupted or not, right? Based on the remainder again, right? So in this particular case, the remainder becomes our frame check sequence. In the other case, it will be our at the receiver end. The remainder should be all zeros in order to indicate no uh, there has been no corruption of the data, right, during transmission. But as it says, we need to find the frame check sequence of 7 bits and write the stream that needs to be transmitted, assuming the polynomial is this, right? So you can see the polynomial, right? Polynomial that we have. The polynomial will be 1 bit longer than the frame check sequence bit, right? So in this particular case, it is 7 bits. So our polynomial should be 8 bits, right? So you can see 1, 2, 3, 4, 5, 6, 7, and 8. So the polynomial that is being used is of 8 bit or 1 bit longer than the frame check sequence usually, right? So the first step of this particular case is in order to find the transmitting frame check sequence, what we do is we are going to be using 7 bits. We need to identify the 7 bits. So we write the data. Okay? We write the data. We forget about this parity bit, right? Our main data is this particular code, right? This is the data that we need to transmit, right? The stream that needs to be transmitted. So we write the stream of data that needs to be transmitted, right? So up till here, right? Our last code is basically 000, so 1000, right? There is a stream of data that we need, and the blue lines, these blue zeros indicates the number. We are basically adding the number of zeros or padding the number of. We need to find the 7-bit frame check sequence, isn't it? So what we do is we pad the data with 7 extra bits, right? If it was a 5-bit or 6-bit frame check sequence, we pad the data with that many bits, right? So in this particular case, we have 7 bits, right? So we add extra 7 zeros, 1, 2, 3, 4, 5, 6, 7. And we start with the first one. The first one we have in our data, the first one that we have in our data stream, right? So in this particular case, the first one is this one, right? We have written the data stream, right? Data stream is what we got from part C over here, right? We write the data stream. We pair it with n number of zeros that depends on this frame check sequence number of bits, right? 37. So we add seven extra, or we pair the data stream with extra 7 zeros, right? So this is what we get. The polynomial that we need to use is 1001, 1001, and modulo 2 arithmetic needs to be used. So modulo 2 arithmetic is basically the exclusive OR operation, right? Okay, exclusive OR. Modulo 2 is basically X OR operation, right? Okay, so we start with the first digit, right? So let's say this is my first digit, the first one that needs to be transmitted uh, uh, in this stream of data, right? So from the first part, so we write 1, right? So at straight under this one, we write 1. We write our stream of polynomial data. That is 1001, 1001, and then we perform the XOR operation. So these two are like bits, so 0, right? We ignore that bit. Again 0, so we ignore the bit. If we have any zeros in front, we ignore those, right? We omit it. We start with always, we write the polynomial, or we start writing the polynomial in order to perform the operation from the first one that needs to be transmitted, or the first one after the operation, right? So in this particular case, The first one was over here. So we started writing our polynomial just under that, right? This is number one. So straight after that, this are likes, so dash, this are likes, again dash. 1 0 will give me 1, 0 1 is going to give me 1, 1 1 is going to give me 0, right? Remember, likes give me 0, unlikes give me 1, right? That's the rule of XOR, right? And then 1 0 is 1, 0 0 is 0 0 is 0, 0 1 is 1, right? So we stop over here, right? So we have what we do. How many bits do we have? 1 2 3 4 5 6, right? Till here, up till this operation, we have 6 bits. And we have how many polynomials? 8 bits, right? So what we do, we carry this one down, right? The bits, right? After this, we have taken the first 8 bits. Now we consider 2 extra bits in order to make this 8 bits, right? So we get this one down, we get this 0 down. So now this data string is 8 bits long. So we start with the first one, right? We write the polynomial starting from the first one over here that we have based on the operation, right? So 1 0 0 1 1 0 0 1. Again, we perform the XOR operation. If we get any zeros in front, we ignore it, right? So these two are likes, it will be 0, right? So we ignore it, right? We create a dash. 1 0 is going to give me 1, 0 0 is going to give me 0, 1 1 is going to give me 0, 0 1 is going to give me 1, 1 0 is going to give me 1, 1 0 is going to give me 1, and 0 1 is going to give me 1. Okay, so I stop here. So now how many bits do we have? 1 2 3 4 5 6 7. We need to make it 8 bits, right? After each operation, we have to carry x number of bits down in order to make that particular sequence 8 bits long, right? So we have 7 bits. What we do? We have taken these 2 bits. Now the next bit is 1. We carry that down, right? So let me erase this. So we are at the point. So we carry this 1 down. So now we write that 1 extra over here, right? We write that 1 extra over here. We carry this 1 down, and then we start with the first one, right? Remember, this one first bit was 0, so we ignored it, right? We don't consider 1. We start with the first one that is going to be transmitted. So now we have 1 0 0 1 1 1 1, and we have carried 1 from here, right? The corresponding 1 from here. So this one has been carried down. Now we start with the polynomial operation again. We write the polynomial with starting with the 1, right? Just underneath the first one that we have, we start writing our polynomial. So we write our polynomial, right? So we have this. So you can see these are likes. So it's all going to give me 0. So there is no use writing this. So we create a dash. So 1 1 is going to give me 0. So dash 0 0 is going to give me 0. Again dash 0 0 is going to give me again 0. So dash 1 1 is going to give me 0. Again dash 1 1 is going to give me 0 again. So again dash. So all these bits are 0. So we can ignore them, right? So 1 0 is going to give me 1. 0 1 is going to give me 1. 1 1 is going to give me 0. So I stop here. So I had carried this one, first one after this blue line, I had already carried it below. So I ignore this. The next is I have 1, 2, 3 bits. So I need to carry 5 bits down, right? So 1, 2, 3, 4, 5. So I'm going to carry 1, 1, 1, 0, 1. So 1, 1, 1, 0, 1. And then I write my polynomial that is this straight under the first one that I've given, right? I start writing my polynomial again. So 1 0 0 1 1 0 0 1. Now, so up till this one, I have already carried it down, right? That is to remember where up till what digit I have carried down, right? So now 1 0 0 1 1 0 0 1 is written, right? This is my polynomial. This is my p. This was my p again. This one was my p again. Now, again, I'll perform my arithmetic 2 operation, or basically the exclusive OR operation over here. In this particular case, again, likes are going to give me 0. So first bit is 0, so we can ignore it, right? Remember, if the first bits are 0, we ignore it, right? So 1 1 is going to give me 0, so I ignore that. 1 0 is going to give me 1, so 0 0 is again going to give me 1. 1 1 is going to give me 0. 1 1 is going to give me 0. 1 0 is going to give me 1. 0 0 is going to give me 0. 1 1 is going to give me 0, right? So how many bits do I have now? 1 2 3 4 5 6 7. So I had carried this up till this 1. I carried it over here. So the next digit after that is 1. So I carry that 1 down in order to make this set of data over here 8 bits, right? So again, I write the same polynomial at the bottom, and again I start my operation. I get this remainder, and then I carry forward those bits, and I keep on doing it until I get the final, right? At the end, so happens at the end I'll get a remainder of 7 bits, right? One less bit compared to the polynomial. So you can see at the last bit over here we have 7 bits. Now we cannot perform the XOR operation over here because we need 8 bits in order to perform the XOR operation with the polynomial, isn't it? So once we have the remaining bits, right? The remainder, once we have the remainder to be 1 bit less than the polynomial, we stop. Okay? Once we have 1 bit less compared to the polynomial, right? This polynomial has 8 bits, right? So the frequency check sequence should be 1 bit less, isn't it? So as soon as we have 7 bits left and no other variable or no other bits to be carried forward, we stop. So in this particular case, we stop at this particular bit. So our frequency check sequence becomes the remainder, right? That we have over here. But remember, in this particular case, there was a 0 again, right? This was a 0, this was a 0. So we had ignored this particular one. So we'd have been left with 1 0 0 0 0 1. Okay, this 2 0 0 would have been ignored, right? This 0 would have been ignored. So we'd have been left with 5, but we need to make, remember, our FSC or frequency, the frame check sequence has to be of 7 bits or 1 bit less than the polynomial. So we add a 0 in order to make this 6 bits of size 7, right? We add a extra 0 in front of this particular remainder that we have in order to make the frequency checksum of size 7, right? Or of 7 bits long, right? Same goes, let's say if we had a polynomial, right? Let's say if this another example that that has been given over here. Let's say our polynomial operation was 6 bits long, so our frequency check not frequency, frame checksum bits would have been 1 bit less than the polynomial. So our polynomial has 6 bits. The frequency the frame check sequence would have been 1 bit less, so that means 5 bits long. So what that means is that we write our data stream, right? This is the data stream that we have, right? Let's say, and we pair it with how many zeros? We pair it with if our FCS is 5 bits long, we paired this particular data stream with 5 extra zeros, right? 1, 2, 3, 4, 5, and then in our then we perform our XOR operation or ATIC2 modulo, right? Remember I said, if we have zeros in front, we ignore them, right? Basically, it does not indicate anything. So writing either 0, 1 or 1 is the same thing, isn't it? 0, 1 has a value of 1. 1 also has a value of 1. So basically, we can ignore the zeros in front. So we start with the first one that is going to be transmitted, right? So the first one over here in this particular case is this. So we write our 1 and we start writing our polynomial just underneath that, right? So in that particular case, our 1 is here. So straight underneath that, we write our polynomial sequence over here. So that is 1 0 0 1 0 1, right? Remember? And then we perform our XOR operation on this. So likes are going to give me 0. So likes are going to give me 0, right? So remember, if we are getting extra zeros in front, we can ignore them, right? So we ignore them. As soon as we get 1, so there is a point where our sequence starts. So we are going to say 0 0 for this, 0 for this. So we can ignore those. And then we have 1, 0. 1, 0, 1, 0 is going to give me 1. 1, 1 is going to give me 0. 1, 0 is going to give me 1. 0, 1 is going to give me 1. So I have, so basically we stop at this particular point, right? We have 1, 2, 3, 4 bits, right? That after the operation of XOR with this first set of uh, a frame, right, or first set of a sequence, we get 4 bits left. So what do we do is since we need to perform an XOR, right, we need to have the same number of bits, right? So we have 4 bits, we carry 2 down. So we carry the next two digits after this, right? We stopped our sequence over here. We perform the XOR with this last 0 over here. The next two bits are 1 and 1. We carry those 2 down. Okay, carry those 2 down, right? So we stop at this particular point. We are so yeah, so this one mistake, excuse me for that. Let's say till this one we are carrying this to 1 down, right? Now we can perform the XOR with this particular polynomial. Again, we write the polynomial starting from the first one that we have. So the first one we have is this one, right? We have ignored these 2 zeros that we have over here. So one is over here, right? So straight underneath, we start writing our polynomial 1, 0, 0, 1, 0, 1. We have carried this to 1 down, so we have carried those to 1 down. We perform our XOR operation. We are going to get this particular data over here up till here. We're basically going to get 1, 1, 0. I mean, 1, 1 is going to give me 0. 0, 0 is going to give me 0. We can ignore those, right? Because if eventually adding zeros in front is not going to make any difference, isn't it? Let's say even for a numerical integer value, you have, let's say 0, 1, 0, 0. We can say this is same as 100, isn't it? Or 100, because this one has no significant value, right? It is not contributing to the value over here that we have these 3 bits over here. Okay, so that is why we are ignoring the 0. So I'll erase that. Okay, so likewise we are just over here. We carried this 1 and 0s down, right? So I'll separate those. So I've carried this 1, 0 down in order to make it 6 bits long. Again, I'm going to write the polynomial starting from the first one that I have. These 2 are zeros, so I can ignore those. The first one that I have, we start writing our polynomial just under that one, right? So we write our polynomial, and then we perform our XOR operation with this, right? Again, we are going to 1, 1 is going to give me 0, 0, 0, 0 is going to give me 0 again. I can ignore those 0, and then 1, 0 is going to give me 1, 1, 0, 1 is going to give me 1, and 1, 0 is going to give me 1, and 0, 1 is going to give me 1 again. So we stop over here. We have how many bits? After this operation, we have 1, 2, 3, 4 bits. So we carry another 2 bits from here, right? So we carry this once at the bottom, and again we write our polynomial starting from the first one that we have after the operation, right? So these values were 0, so I have no those, right? And starting from the first one, straight under this, I'm going to write my polynomial. So I'm going to repeat these steps, right? So you repeat your steps until you are left with less than 6 bits, right? Until you are left with less than 6 bits. Or you have, even if you have 6 bits, but the first bit is 0, right? You repeat this until you have 1 bit less, right? Remember, when I mean 1 bit less, what you mean is you're starting from the first one in your remainder, right? Like I did in this particular case, remainder was this one. So in this particular case, I can ignore the extra zeros in front, right? Because my original data will be just 1, 0, 1, 1. If I add extra zeros, that does not change the value of the data stream, isn't it? So in this particular case, the data set was left as 4. Okay, and you continue doing this operation until you have 1 bit less than this, right? And the starting of this operation should be with 1, right? So I continue doing that operation. I'm going to, at the end, I'm going to be left with this set of data, 1010, right? These zeros can be ignored. So I have 1010. Remember, our frame frame check sequence has to be 1 bit less than this polynomial. So it has to be 5 bits long. So I have a data of 1010. So I paid it with 1 extra 0 in order to make our FCS 5 bits long, right? So 01010. Okay. So that's how you perform your that's how you find your frame check sequence. So basically, you have a data set. You paid n number of zeros. So n number of zeros are basically, when I mean n, it is the number of bits that is going to represent your frame check sequence, right? So that is going to be written over here, right? Adding that extra number of zeros, and then you start writing your polynomial straight under the first zero, the first one that you have, right? First one that is going to be transmitted. So in this particular case, it was 1. In this particular case, all this was 0. So we start with this is the first one that is going to be transmitted, isn't it? So straight under that, you write our polynomial that needs the polynomial that is going to encode the transmitting signal, right? Okay, and you keep on doing it, right? At each step, if you have zeros in front, after performing the XOR operation, right? Remember, in this particular case, after performing the XOR operation, if I have any zero, you ignore those, right? You start with the first one, right? You only write the data starting from the first one that you get in that particular operation. And then you stop, you check how many bits you have, you compare it with your polynomial that you have, that you are performing the operation with, okay? If it's less, you carry those the required number of bits from the data over here, right? The data you carry it out, and then again you write the polynomial starting from the first one, and then you perform your XOR operation, right? XOR operation represents the modulo 2 arithmetic, right? So with that, we'll come to a conclusion, right? So I'll end this particular tutorial over here, right? And after this, we'll have a question answer session, right? So I'll stop this recording over here, and then we'll have a session. Whatever queries you have, I'm going to try resolving those, right? Okay. So uh, that's regarding the switch tutorial. So thank you for joining me, right? So I'll stop the recording over here, and then have our uh, discussions or whatever queries you have. Okay. Remember, this was just an example. This was part of this calculation is part of the question that we have over here. So this is just an example. Okay. Okay. So with this, I'll stop recording and we'll have our discussion session. Thank you.